Hello, and welcome to the lesson on section 12.6, Absolute Convergence and the Ratio Test. In this lesson, you'll learn what it means to be absolutely or conditionally convergent, and how to determine whether a series can be classified in this way. We'll also look at two other tests for convergence, the ratio test and the root test. A series is absolutely convergent if the series formed by the absolute values of its terms converges. The alternating series -1 to the n plus 1 over n squared is an example of an absolutely convergent series. The series formed by its absolute values is a p-series with p greater than 1. A series is called conditionally convergent if it converges but is not absolutely convergent. The alternating harmonic series is a classic example of conditional convergence. The harmonic series diverges, while the alternating harmonic series converges. If a series with terms a sub n is absolutely convergent, then it is also convergent. Here's a quick proof. First, if I add any term to its absolute value, the result will either be 0 if a sub n is negative, or 2 times the absolute value of a sub n if a sub n is positive. By definition, if the series a sub n is absolutely convergent, then the sum of the absolute values converges. Then the sum of 2 times the absolute values also converges, because we're just multiplying by a constant. So I've shown that a series with larger terms converges. Thus, by the comparison test, the sum of a sub n plus the absolute value of a sub n converges. Subtracting two convergent series results in the sum of a sub n. The difference between these two series must converge. Therefore, the series a sub n must also converge. So far, we've looked at the integral test, the comparison and limit comparison tests, and the alternating series test. This is the ratio test. Suppose we form a ratio between the n plus first and nth terms of a series. If the limit of the absolute value of this ratio, as n approaches infinity, goes to some real number L, then the series with terms a sub n absolutely converges if L is less than 1, or diverges if L is greater than 1. The ratio test is inconclusive if L equals 1. In this case, we'd need to use one of the other tests for convergence instead. We won't be proving the ratio test together, but I'll discuss it informally. Recall that an infinite geometric series converges when its common ratio is less than 1 and diverges when its common ratio is greater than 1. In the ratio test, there isn't a common ratio if it's not geometric, but we look at whether the ratio between terms approaches a number less than 1 or greater than 1 and arrive at the same conclusions. Let's look at why the ratio test is inconclusive when the limit is equal to 1. First, consider the harmonic series. The limit of the ratio of the n plus first term to the nth term is 1. For the p-series with p equal 2, the ratio between terms also has a limit of 1. So here we have two different series that came out to a limit of 1 by the ratio test. We already know that the series on the left diverges and the series on the right converges. Thus, finding a ratio limit of 1 did nothing to help us determine whether these series converged or diverged. In these examples, I'll show how to use the ratio test to determine whether each series converges. First, find the limit as n approaches infinity of the absolute value of the n plus first term divided by the nth term of the series. Find the n plus first term by replacing the n's in the formula with n plus 1's. I usually write the division as multiplication by the reciprocal, since these ratios often involve division of two fractions. Find the limit by gathering together and reducing parts that are alike. I gathered the n squared and the n plus 1 squared together, and 1.1 to the n plus 1 divided by 1.1 to the n results in 1.1. The limit of n squared over n plus 1 squared goes to 1, so this makes my limit 1 times 1.1, which is greater than 1. So by the ratio test, this series diverges. Now on to the second series of the example. Here's the limit of the ratio between terms. N factorial over n plus 1 factorial reduces to 1 over n plus 1, and I've gathered the rest of the fraction on the left there. The denominator has a larger degree, so this limit will go to 0, which is less than 1, so the series is absolutely convergent and thus converges. For the third series in this example, here's the limit of the ratio between terms. The limit of n over n plus 1 goes to 1, and I can use L'Hopital's rule to show that the limit of the natural log of n over the natural log of n plus 1 also goes to 1. So the limit is 1. And my results here are inconclusive. At this point, we'd move to another test for convergence, such as the integral test or the comparison test, but I'll leave this to you as an exercise if you like. The root test is not an official AP topic, but it's very similar to the ratio test, and so not that difficult to add to our bank of strategies for testing for convergence. Notice that the conclusions are the same as the ratio test, but we find the limit of the nth root of the absolute value of terms instead of the ratio between terms. I'll use the root test to determine whether these two series converge. Find the limit of the nth root of the absolute value of the nth term. This limit goes to a number greater than 1, which means that this series diverges. Here's the limit of the nth root for the second example. Since this goes to a number less than 1, the series converges. This concludes the lesson on section 12.6, the ratio test.